Hello everyone, this is Meghna. I'm the group representative for the batch number 109. I'm going to present a topic on a technique for detecting diabetic retinopathy at all stages using deep learning. Here are the contents: introduction, literature survey, proposed system, results, conclusion, followed with references. Coming to the introduction. Diabetic retinopathy, which is also abbreviated as DR, is an eye disease that leads to vision loss and also blindness to people who have severe diabetes. It is caused by the damage to the blood vessels of the retina. So, DR is oftenly known as diabetic eye disease. It is a condition where there is a damage to the retina as a result of diabetes mellitus. So, diabetic retinopathy is a key cause of blindness in the working age population. It is categorized as two types, as type 1 diabetes and type 2 diabetes. DR can occur up to 80% of those who have had type 1 or type 2 diabetes for 20 years or more. The eye's vision is impacted by several issues. You can run a higher chance of developing type 2 diabetes if your blood sugar levels are higher than average. Early disease detection improves the effectiveness of treatment in the healthcare industry. The method for determining whether the patient has diabetic retinopathy or not involves offering a user friendly interface. It improves the performance of neural networks with extra layers using inception resistant V2 architecture. It is categorized as follows: no DR, mild, moderate, severe, and proliferative. Mild, non-proliferative diabetic retinopathy, which is associated with the growth of microenzymes in the retina of the eye. It is the first stage of the disease. Moderate, non-proliferative retinopathy, where the blood vessels in the retina may enlarge and change as the condition worsens, and results in losing their ability to carry blood. So the retina receives less blood due to severe diabetic retinopathy because more blood vessels are blocked, which signals the retina to grow new blood vessels. And coming to the last stage, which is proliferative diabetic retinopathy, this is the disease advanced stage. It is identified by the stimulation of new blood vessel growth along the inner surface of the retina. So therefore, determining the stage of DR requires a proper diagnosis. Coming to the literature survey, here we have surveyed a couple of papers which involves the various techniques in diagnosing the DR, and one paper is also followed with only binary classification, which is stated as whether a patient has DR or not. But ours used is the multi classification, which not only tells a patient is diagnosed with DR, but also it tells at what stage it is exactly in it. Coming to the data pre-processing. The data pre-processing is the major part used in our technique. Here there are two images shown. The first image is the original fundus image and the second image is the pre-processed image. The first image is before pre-processing has done. Coming to the second image, which is clearly seen that the pre-processing has happened, which results in removing the black portions of the image. Also, the image is brightened up. So what exactly happens during pre-processing is that the black portions in the image are removed using a filtering approach during data pre-processing. So the primary step in picture pre-processing is the feature extraction. It is a procedure where the original data's limitation are reduced in number. It is helpful in representing the original data in an informative way. So here the extracted images are taken into consideration to classify the type of hemorrhages used. So it also involves various processes like scaling, shifting, rotating, etc. So by doing all such factors also, the data pre-processing happens. Now coming to the proposed system architecture, which is inception resistant V2 architecture. Now before we get into the details of the architecture, let's come up with the question, why the inception resistant V2 architecture has been chosen. So Inception Net is found to be better over all other CNN models by observing efficient utilization of the computational resources, where we can expect the high performance output. So InceptionNet achieves an accuracy of top 5 on ImageNet, and it reduces the computational cost, giving high speed and accuracy. It is also used for the dimension reduction. It is done by increasing the number of channels. By adding 3 of 1 by 1 convolution layers, when we get into deep into the architecture, we'll get to know the channels, how they are, uh, how the number of channels are increased by adding the convolution layers. And the another benefit of using inception architecture is that it reduces the problem of overfitting. What is overfitting? It starts memorizing the things instead of learning. That is, the testing errors are more. So, by using this architecture, the overfitting problem will be reduced to a great extent. Also, it reduces the number of parameters. That is, the data will be less, and computational resources also will be less. Now, coming to the details of each block. It starts with the input layer. Here we apply the input images to the input layer, and the resizing of image is done into different dimensions. Convolution layer. The convolution layers, in basic words, it applies a filter to an input image which results in the activation of the input image. So once a feature map is created using multiple filters, it can be passed through the activation function such as ReLU. ReLU is abbreviated as rectified linear unit. So the usage of ReLU helps to prevent the exponential growth in the computation which is required to operate in the neural network. Max pool layer. The main purpose of using a max pool layer in a CNN is to minimize the dimensionality of the feature map. Average pool layer. So in order to construct a downsampled feature map, the average value for patches of a feature map is calculated using average pooling method. It is frequently applied following a convolution layer. Concatenation. In basic words, the output of one concatenation layer is applied as the input to the next concatenation layer. So it combines all the outputs and feature maps from the convolution filters, and it groups into a single object. Residual. Artificial neural networks include the residual neural networks connections, which is also called as ResNet. By placing numerous residual blocks on top of one another, a residual network is created. So the remaining blocks establish an identity that corresponds to network activations from previous stages. Fully connected layer. Here we activate the ReLU function on the layers that are completely interconnected. Softmax. Softmax is an activation function. It is a standard nonlinear activation used widely for the classification problems in deep learning architectures. The output produced by the completely connected layers output has the dropout subjected to the softmax activation function. These convolution layers allows us to categorize the images. Dropout. The extremely basic concept of dropout is utilized to prevent the problem of overfitting. Each time a neuron iterates during training period with probability p, it is momentarily dropped or inhibited. This indicates that at the current iteration, all of the neurons' inputs and outputs will be disabled. At every training step, the dropped out neurons are resampled with the probability p, allowing a dropped out neuron at one step to be active at the following one. So the dropped out rate, also known as the hyperparameter, is normally in the range of 0.5 or 50% of the neurons, and it is one of the hyperparameters. So these are all the layers involved in the inception resistant V2 architecture. Coming to the results and discussions. Here we have used the Aptos dataset, which is made available on the Kaggle website. It is widely used in the computation for the DR detection. So each image can be classified into 5 different clusters based on the dataset. like no DR, mild, moderate, severe, and proliferative. Here, all the testing and training images are divided. So all the images are divided as testing and training images. There are 368 testing images and 3294 are, are training images are used. Coming to the classification of test data. Here we have considered certain performance metrics like precision, recall, F1 score, support under each class, starting from no DR to proliferative, and the weighted average is being calculated. Now we are comparing our proposed model with the already e- existing model results. Here it can be clearly seen that the existing model, which is Inception V3, and our proposed model, that is Inception ResNet V2, there is a slightly change in the values of performance metrics. The accuracy attained on the training set is detailed by the training accuracy. So the multi-classification training accuracy from this model is 81%. The accuracy attained on a testing set is known as validation accuracy. This model yielded a validation accuracy of 81.5% and specificity of 94.3% is obtained from this model. Now coming to the conclusion. This study developed a typical CNN architecture and it is suggested a CNN approach to diabetic retinopathy. To a level that we are aware, this is the highest numerical accuracy obtained by automated diabetic retinopathy detection model. So finally, we have obtained 81.5% validation accuracy and it is reached for 100 epochs. Here we have tried to classify the no DR images as well. This research described in this paper is meant to help the diabetic patients in maintaining the level of medical care of the retina. Here are some references used. Thank you.